Welcome to the Deep Dive. Today, we're digging into something really fundamental, a core limitation affecting pretty much every large language model, every generative AI tool you might be using. The source material calls it backward AI.
That's right. And it's a crucial distinction. Current Gen AI, it's fantastic at finding correlations in huge piles of past data. It spots patterns, finishes your sentences, makes things look complex.
Yeah.
But, and this is the key thing, it's fundamentally chained to the past. It's just rehashing what has happened, not really predicting what will happen based on cause and effect.
And that's the root of things like bias or those, weird hallucinations everyone talks about.
Exactly. That reliance on correlation over causation.
Yeah.
It breaks down when things get unpredictable or new.
Okay, so our mission today is to explore some fascinating source material that actually maps out a path toward what it calls forward AI, AI based on causation.
And the way they got there is,
Yeah.
oh, it's pretty wild. They used a multi-AI agent's meta-analysis.
Meaning they got AI to critique itself.
Essentially, yes. They took leading systems, Grok, Copilot, ChatGPT, others, and basically commissioned them to analyze their own inherent design flaws and even propose a fix.
Wow. Okay, so what did the AIs themselves propose?
They landed on something really out there, blending current tech with quantum physics, quantum augmented self-adaptive networks. QASANs for short.
QASANs, right.
And the promise is that these QASANs could potentially solve a kind of trilemma that current LLMs just can't crack, achieving real agility, resilience, and sustainability all at once.
All right, let's unpack that. Because if you rely on AI for, well, anything important, understanding why it sometimes fails is critical. The sources pin the blame for this backward AI problem squarely on the foundations.
Yeah, the transformer architectures, the deep learning models, combined with how they're fine-tuned using reinforcement learning, or RL.
Okay, RL.
RL is great for learning a specific task in a stable setting, but it leans heavily on two core algorithms, stochastic gradient descent, SGD, and backpropagation.
Can you give us the quick version of what those do?
Sure. So think of backpropagation as the system's way of figuring out where it went wrong. It traces errors back through the network to see which connections need tweaking.
And SGD.
SGD is the mechanism that actually makes the tweaks. It's the step-by-step learning process, adjusting things iteratively based on new data. But it does this based on, well, gradients, like slopes on a map.
Got it. And the sources argue these two core parts, SGD and backpropagation, are basically guaranteed to fail predictably when things get messy, under uncertainty.
Precisely. The analysis highlights three key areas where they stumble. Let's start with what happens when the environment itself is constantly changing, what the sources call dynamic uncertainty.
Like trying to use AI in, say, a volatile market or a rapidly evolving situation.
Exactly that. In those kinds of non-stationary environments, SGD really struggles. The meta-analysis actually showed about 85% agreement among the AI agents themselves that SGD suffers from this non-stationarity.
What does that mean practically? It just gets confused.
It causes oscillations in the parameter updates. Imagine you're steering a ship, but the current keeps changing direction unpredictably. You'd constantly be overcorrecting, swinging back and forth. That's SGD.
Okay, constant overcorrection. And backpropagation plays a role too.
Yeah, it contributes by leading to what's called overfitting shifts. About 80% agent agreement on this one. The model gets too tuned to the recent past data. So when the underlying reality shifts, it fails to generalize. It's stuck on old patterns.
And the consequence, what's the measurable impact?
The sources point to a predictable failure, around a 35% degradation in policy effectiveness in these dynamic environments.
Yeah.
So its decision-making quality drops by more than a third when things get unstable.
That's not great for critical applications. Okay, what's the second dimension of failure? Adversarial uncertainty.
Right. This is about deliberate attacks or manipulation. Think poisoned data or carefully crafted prompts designed to trick the AI.
Like prompt injection attacks we hear about.
Exactly. And here, backpropagation shows a specific weakness: vanishing gradients. This came up with 82% agent agreement.
Vanishing gradients? Sounds like it just stops learning.
Pretty much. Under an adversarial attack, the error signal, the information telling the model how wrong it is, becomes incredibly tiny, effectively zero. You can't feel the error anymore, so it can't correct itself. It's like the nerves are deadened.
And SGD, how does it cope under attack?
It faces a different issue: noisy gradients. About 75% of agents agreed on this. Instead of a clear signal pointing towards the right correction, it gets a blast of static, contradictory information.
So it doesn't know which way to adjust.
Right. It either freezes or makes random, unhelpful changes.
And the result of these vanishing and noisy gradients, how bad is the performance hit?
It's severe. The analysis points to a 45% drop in accuracy when under adversarial attacks, a huge vulnerability.
Wow, nearly half its accuracy gone. Okay, so dynamic uncertainty, adversarial attacks. What's the third failure point?
It's a more practical one, but still fundamental. Time-space complexity, basically issues of scale and speed. This connects to something called a curse of dimensionality.
Right, the curse of dimensionality. That sounds pretty ominous. Can you break that down for us?
Think about the space the AI operates in. It's defined by potentially billions or even trillions of parameters or dimensions. As you add more dimensions, the volume of that space grows exponentially.
Okay.
So trying to find meaningful patterns or causal links in that vast space requires an astronomical amount of data and computing power. It becomes computationally prohibitive, especially for real-time tasks needing forward prediction, not just backward correlation. About 60–65% of the agents flag this.
So basically, SGD and backpropagation, the core learning mechanisms, are flawed when things change, when they're attacked, and they struggle to scale efficiently for the kind of forward-looking tasks we actually need.
That's the core argument from the sources, yes. These algorithms are brilliant pattern matchers for static historical data, but inherently brittle under real-world uncertainty.
Which brings us back to that really unique methodology, the multi-AI agents meta-analysis. How exactly did they use these AI systems to find a solution?
It's a fascinating approach because it wasn't just about crunching numbers. They used 6 top AI agents: Grok, Copilot, ChatGPT, U.com, Perplexity, Gemini, and tasked them with this deep self-critique, but guided by a specific philosophical framework.
Philosophy. You mentioned critical relativism. Why bring philosophy into AI algorithm design? Seems a bit abstract.
It sounds it, but it was apparently key to forcing a breakthrough. It's based on inquiring systems philosophy, designed to push beyond just finding consensus towards generating genuinely new, even revolutionary ideas. It had 4 phases.
Okay, walk us through them. Phase 1 and 2.
Phases 1 and 2 were grounded in what they called Lockean empiricism and Leibnizian rationalism.
Okay, less academic terms.
Right. So first, like Locke, the AIs gathered empirical evidence facts about their own failures, just raw data collection on where they messed up. Then, like Leibniz, they used logic and reasoning to build consensus from those facts. That's where you get findings like the 85% agreement on SGD's non-stationarity problem. They logically deduced from the evidence that relying on backward-looking correlations must lead to failure when predicting forward causation.
So phases 1 and 2 establish consensus on what was broken and why. But that doesn't invent a solution. What about phases 3 and 4?
That's where it gets really interesting. Phase 3 was Hegelian dialectics.
Meaning conflict, arguments.
Pretty much. Instead of seeking agreement, this phase focused on identifying and amplifying the disagreements, the contradictions, the most radical critiques the AIs had of each other and themselves, creating tension.
So the AIs were kind of debating the fundamental nature of their own limitations.
In a structured way, yes.
Yeah.
They weren't just agreeing, they were challenging assumptions. And it was that structured conflict, that dialectic, that led to phase 4, the Kantian synthesis.
The big idea.
The transcendental critique. The realization that the failures weren't just minor bugs, they were fundamental flaws in the classical computing paradigm when applied to causal uncertainty. The conclusion was that these predictable failures demanded a completely different kind of logic, a quantum dialectic. And that synthesis pointed directly towards QASANs.
They essentially reasoned their way out of classical limitations and into quantum possibilities. Can we connect that back to specific AIs?
Sure.
How did, say, Grok or Copilot's critiques lead to specific quantum fixes within the QASAN idea?
Absolutely. Let's take Grok. Its analysis really zeroed in on those SGD oscillations, the overcorrection problem in dynamic situations.
Right.
The QASAN solution it pointed towards uses quantum superposition.
Okay, superposition allows quantum bits to be 0 and 1 at the same time. How does that help?
It means instead of the classical AI trying one possible parameter update then another sequentially, the QASAN, using superposition, can explore all potential causal paths simultaneously, like checking every possible route on a map instantly. It bypasses the oscillation issue.
Okay, parallel exploration. What about Copilot? It focused on the adversarial attacks, right?
Yes, the vulnerability to manipulation. Copilot highlighted how easily the causal links within the model could be broken or perturbed.
And the quantum fix.
Quantum entanglement. This links variables together in a deep, non-local way. If you encode the causal relationships using entanglement, they become incredibly robust. Messing with one part instantly affects the others in a predictable way, making the whole causal graph resistant to tampering.
Entanglement for security.
Yeah,
Cool. And ChatGPT, it tackled the scaling problem, the curse of dimensionality.
it did. For that massive time-space complexity issue, the proposed solution involved Grover's algorithm, or Grover's speedup.
Which is a quantum search algorithm.
Exactly. It offers potentially exponential speedup for searching through huge, unstructured data sets or state spaces. It's the key to making causal discovery computationally feasible, even with billions of parameters.
Makes sense. And finally, Gemini. Its critique was about delayed feedback in RL.
Right. Many RL systems learn slowly because the consequences of an action only become clear much later. Gemini's analysis suggested using quantum annealing.
Annealing. That's about finding the best solution, the lowest energy state.
Precisely. Quantum annealing is particularly good at finding optimal solutions in really complex, bumpy landscapes quickly. Applying it allows QASANs to optimize their policies much faster, closer to real time, which is vital for things like, say, dynamic medical diagnosis or control systems.
So each AI's critique of a specific classical failing pointed towards a corresponding quantum mechanism superposition, entanglement, Grover's, annealing that could potentially solve it. This really does sound like a fundamental redesign.
It is. It's why the sources frame QASAN's quantum-augmented self-adaptive networks as a paradigm shift. It's about moving towards truly causal, resilient AI, pioneering post-AI quantum futures, as they put it.
Okay, let's get concrete about QASANs. You mentioned 3 pillars they integrate.
Yes, it's not just about the quantum hardware. Pillar 1 is the hardware, though. Augmented human-machine quantum computing AI. This leverages superposition and entanglement for that massive parallel processing and optimization needed for genuine causal modeling. Things classical computers just can't really do at scale.
Okay, quantum power. What's pillar 2? It sounded like it addressed the meaning aspect, the hallucination problem.
It does. It's called human-centered meaning-aware AI, or quantum minds. This is crucial. It's about embedding human intuition, creativity, ethics, meaning directly into the AI's learning and reasoning process.
So not just data patterns, but human context and values.
Exactly. The goal isn't just accuracy based on correlation, but understanding and judgment grounded in human meaning. It acts as a guide for the AI's causal search.
Interesting. And the third pillar. It seemed linked to adaptability, handling that dynamic uncertainty.
That's self-adaptive complex systems, or SCCS. This provides dynamic resilience and evolution. It allows the QASAN network to constantly monitor its own performance, learn from errors, and crucially reconfigure itself in response to changes or uncertainties in the environment.
So it can literally change its own structure to stay effective.
Yes, it adapts its internal causal graph to match the complexity of the world it's interacting with. True self-adaptation.
Okay, so we've got the quantum compute power, the human meaning layer, and the self-adapting structure. Did this combination actually deliver in tests? Did the simulations show QASANs achieving that trilemma of agility, resilience, and sustainability?
According to the source material simulations focusing on LLM discovery tasks, the results were quite promising. For agility, using quantum parallelism.
The superposition trick.
Right. They reported up to a 3x speedup compared to classical approaches on the same tasks.
That's a significant jump. Addresses the time complexity issue directly. What about resilience to those adversarial attacks?
Resilience, attributed largely to the entanglement protecting the causal structure, showed a reported 30% gain against perturbations.
Okay, so that eats into that 45% accuracy drop we talked about earlier. Not eliminated, but much better.
A definite improvement. And for sustainability.
How did they measure that?
Through the SACS pillar. The self-adaptation allowed for things like adaptive sparsity, basically, turning off parts of the network that weren't needed for a specific task and reducing computational complexity over time, making it more efficient.
Makes sense. But the big goal was causation, moving beyond correlation. Did they show QASANs could actually do that better?
That was the headline result, really. In benchmarks specifically designed to test causal discovery in non-stationary environments that changed the QASAN LLMs reportedly outperformed classical AI by 40%.
40% better at finding actual cause and effect in shifting conditions. That does feel like a different kind of AI.
It's the difference between predicting the next likely word based on statistics and predicting an actual outcome based on understanding the underlying causal forces.
And this capability, this resilient causal reasoning, opens up applications where current AI is maybe too brittle.
Exactly. The sources mention things like causal risk modeling in finance, understanding why markets might crash, not just correlating past movements, or high-fidelity adversarial simulations for defense, and dynamic diagnostics in healthcare, where understanding the causal chain of symptoms is literally life or death.
It sounds like, as the sources put it, Schumpeterian creative destruction for the current way of doing AI, a necessary shakeup.
That's the idea. Moving from fragile correlation engines to robust causation finders, embracing the quantum uncertainty rather than being broken by it.
And it's worth circling back to the process here, using multiple AIs to critique each other, guided by this philosophical framework and incorporating human oversight. That seems designed to combat bias, right?
Yes, the transparency of the meta-analysis itself is presented as a way to mitigate the kind of hidden biases you might get from a single AI model or a single human team. Forcing dissent and integrating human creativity is built in as an ethical safeguard.
But, like any cutting-edge research, this isn't market-ready tomorrow. The sources acknowledge limitations, right? We need to be realistic.
Absolutely. They're quite clear on the caveats. Firstly, we're still in the NAQ era, noisy intermediate scale quantum computing.
Meaning today's quantum computers are imperfect, prone to errors.
Yes, so the simulations likely rely on approximations of true quantum computation. The full power of QASANs might require more mature, fault-tolerant quantum hardware, which we don't quite have yet.
Okay, NSQ limitations. What else?
There's the potential bias from the meta-analysis itself. They used only 6 specific AI agents, and the queries were primarily English-centric. So the initial critiques might carry linguistic or model-specific biases.
A fair point. And the noise issue in quantum computing generally.
It's a huge practical challenge. Quantum states are incredibly delicate. Errors can creep in and amplify easily. So for the foreseeable future, managing QASANs likely means complex hybrid systems carefully combining classical and quantum resources to mitigate noise and ensure reliability. It's definitely a gradual transition, not flipping a switch.
So this has been a deep dive into a potential future for AI, one moving from backward correlation to forward causation, using quantum mechanics and a unique self-critique process. It leaves us with a really interesting thought for you, the listener, especially thinking about that quantum minds pillar and the role of human intuition.
Yeah, Albert Einstein famously said, imagination is more important than knowledge. Current LLMs possess vast knowledge, mountains of correlated data, but they lack genuine imagination, true intuition.
Uh-huh.
Now consider this QASAN framework. It explicitly places human creativity, intuition meaning at the center, augmenting potentially the most powerful computational tools we could build. It suggests the future isn't just about making algorithms faster at crunching data.
But about building systems that amplify human insight.
Just exactly. Systems designed not just to find correlations, but to partner with us in the imaginative leaps needed for true discovery, for understanding causation. So a question for you becomes, if AI evolves towards being a partner in causal discovery, how does that change your role, your unique human contribution in driving science, innovation, or whatever field you're in moving forward?